All right, we're back. We're still on page 3 of note 6. We are doing the limit comparison test now, which is a personal favorite of mine. And basically what we do is we have to come up with a series. So you're given a series to work with, you come up with a series you'd rather work with, and then you see what happens to the limit of basically the ratio of the nth terms. If you get a positive finite as you go to infinity, then they both do the same thing. So it's pretty easy to remember the conclusion. The hard part initially, I think, is working out what to compare it to. So if I'm looking at problem C, I think that for really big n values, what has an impact on the numerator? Well, there's only one thing in the numerator, so that'd be that. What has an impact on the denominator? If n is really, it doesn't even really need to be very big. N squared is dominating, so I'm going to use just n squared. So you basically get rid of all the extra garbage. So this is going to give me 1 over n to the 3/2, which is a convergent p series. So I know that this converges. So when I do the limit comparison test, if I get a positive finite, which I'm definitely going to, they both do the same thing. So it's kind of weird. You have to be able to build the series. If you can build the series you're going to compare to, you basically know what's going to happen, which is why it's easier to use than the direct comparison test, because then I'd have to worry, is the given thing bigger than the thing that I came up with, in which case the thing I came up with is useless because I'm trying to show convergence, or is the given thing smaller? I don't need to worry about that with the limit comparison test, which is what makes it a little easier to use. So here, make this n to the 1/2. So I'm just going to multiply by the reciprocal, which actually you'll find you do kind of a lot of with the limit, with the series test, is what I'm trying to say. Plus 1, which is just 1. So 1 is positive and finite. Since it's positive and finite, they do the same thing. So now I have to say what happened. So since 1 to infinity of 1 over n to the 3/2 converges, p equals 3/2, which is greater than 1. The sum 1 to infinity of the square root of n over n squared plus 1 converges by limit comparison test. It's really like, what am I spelling here? Comp test. It's really one of the better tests to use. I mean, it's just straightforward, not a problem. So here's one, for example, right? If say you wanted to try to do direct comparison, you kind of immediately run into an issue because 2 to the n minus 5 is less than or equal to 2 to the n. So 1 over 2 to the n minus 5 is greater than or equal to 1 over 2 to the n. But the sum of 1 over 2 to the n is a convergent geometric. So since it converges, we would need it to be bigger so that it could trap the series we're working with. Limit comparison is going to get us around that. What I'm going to do is I'm going to compare it to 1 over 2 to the n. Because it basically looks like 1 over 2 to the n. Where something weird happened. You know, somebody showed up, they were like, hey, what happens if I do this? And it messes up the beauty of it. So then we got to do this. So I'm going to do 1 over 2 to the n minus 5 divided by 1 over 2 to the n, but I'm just going to write times 2 to the n over 1, which is n approved. You can basically engineer these so that you always get 1 as your limit. I don't really try to do that, but you know, it'll happen a lot. So this is going to give us 1, which is in fact positive and finite. And since it's positive and finite, they do the same thing. So what do? Well, since 1 over 2 to the n converges, and why does it converge? It's geometric. R equals 1/2, which is less than 1. We know that the given series, 1 over 2 to the n minus 5, also converges by limit comparison test. So once you know what you're doing, it's pretty straightforward. I'm just going to finish these, hopefully. What to compare this to? All right, so when things are huge, what matters, right? That's the question. So I'm gonna go against the numerator. I'm gonna leave as n times 3 to the n times 3 to the n over the denominator. The most important part is n to the fourth. So I'm just going to use n to the fourth. I mean, it's 5n to the fourth, but it doesn't make a difference. That's constant multiple. So I'm just going to go with n to the fourth. So this is just going to be 3 to the n over n cubed. So now I kind of have an issue because I don't immediately know if that converges or diverges. We do know what happens to that though, because why do we know? Oh, the limit's not 0, right? The limit of 3 to the n over n cubed is infinity, which means limit's not 0, therefore n-term test for divergence, this definitely diverges. So let me actually, I'm actually going to do that as kind of like a separate little problem here. So I'm going to say the limit as n approaches infinity of 3 to the n over n cubed is infinity, not 0. Therefore, the sum of 3 to the n over n cubed diverges by nth term. Diverges. Okay, by nth term test for divergence. I don't really think you need to write that, but you could if you're in doubt, always write things. But also like put yourself in a position where you're not in doubt all that often, so that you don't have to like overwrite. So we're gonna do this. And then I'm going to multiply by the reciprocal of the other thing, because I'm supposed to divide by it. And then this, so kind of like the magical thing that happens is, I guess I'll write it. I didn't want to. I was going to say, like, we already know what's happening. You get n to the fourth, 3 to the n, over 5n to the fourth, 3 to the n, plus 3n times 3 to the n, minus 2 times 3 to the n. Now, as we go to infinity, the only thing that really matters are the dominant terms. So the dominant terms are this and this. And because of the way they work, we just get 1/5, which is positive infinite. So they do the same thing. So this one had like that extra step because we had to show that the series we were comparing to diverges. Like sometimes you have to do like a couple of extra steps, which is really annoying, but you know, no way around it. So let's say since 3 to the n over n cube diverges, I'm gonna say by nth term test. The series that we started with, which was, what is it? N times 3 to the n over 5n to the fourth plus 3n minus 2 diverges by limit comparison. All right, nailed it. So that does that. This next one looks like it's going to be a little bit easier because think about your dominant terms. Like what really, really matters here is this. What really, really matters here is this. So we're going to compare it to the things that matter. So n over n times radical n is just 1 over radical n, which I know diverges because p is 1/2, which is less than 1. Okay, so I know that this diverges. So actually, I already know the whole thing diverges. Like, it definitely diverges, but let's do the work. So the limit as n approaches infinity, n plus 1 over, I'm going to say n to the 3/2 times radical n over 1 is the limit as n approaches infinity of, so we get n to the 3/2 plus n to the 1/2, which isn't contributing as you go to infinity. To the 3/2. So like what's dominant, what really matters? This and this. Everything else, as you go to infinity, just falls away to kind of meaninglessness. So this is one, which is positive and finite. All right, so let's write our response. So since the sum of 1 over root n diverges, p equals 1/2 less than 1, the sum from 1 to infinity of n plus 1. So it's really like the limit comparison test is kind of, it's kind of like your first thing that you do is ignore most of the given thing. And you just look at the dominant term in the numerator, dominant term in the denominator, and then you do your limit. But like you already know that the limit's going to, depending on how you choose things, the limit will almost always equal 1, or just some, some finite scalar of that. When that doesn't happen, you just set it up wrong usually. Or maybe the limit comparison test doesn't apply because maybe it's too complicated, or I don't know. Like I can think of a lot of reasons why you might not be able to do it. The limit might be too hard to do. Who knows? But anyway, this diverges by limit comparison test, which is truly one of the better tests to use. Assuming you're good at taking limits, which like you should be. Most of these you can do just by thinking. When in doubt, you can use L'Hopital's rule because they almost always give you infinity over infinity. However you want to do it. But if you can work out like what did the series start at before people started messing around with it, that's what you want to compare it to. Preferably it will be a geometric series or it will be a P series because those are the easiest to work with. Like here on part E, we didn't get either of those, but we got a divergent series, which we could show by the nth term test. Just take the limit. So it all comes down to limits. Anyway, I'm going to stop this here, and I will come back in the next video and maybe finish the notes. I don't know what's on the next page, but see you there.